Welcome back, everyone. Today, we are going to be tackling word problems. And I know word problems are always kind of scary in a math class. I definitely understand where that comes from. These ones are going to be a little different than what you're used to. When we talk about the area of a circle, hopefully we know that that's pi r squared. Now, here's the thing. For this first example, oil is spilling from a ruptured tanker spreads in a circle on the surface of the ocean. So we have a circle, and it says the radius of the spill increases at a rate of 8 meters per minute. Now, A in this case is actually a function of time. R is also a function of time. So we're not going to view that the area depends on the radius, but we're going to view that the area and the radius both depend on time. So when we take the derivative, we're going to get the change in the radius with respect to time. And that's what this is. This is increasing at 8 meters per minute. So what this means with the circle is that the radius r is changing because more and more oil is spilling into it. And so the area is also changing and getting larger. So when I take the area of a circle, we're actually going to have to do implicit differentiation to get this. This is going to be dA over dt, which is actually what we're looking for. How fast is the area increasing? And the derivative of this with respect to t is going to give us 2 pi r, then dr dt. Again, remember r is a function of t. Now we're looking for this dA over dt, how fast the area is changing, increasing in this case. And they want to know specifically when r is 7. So this becomes 2 times pi times 7 times dr dt, which is 8. And that is going to give us, when we multiply all that together, 112 pi square meters per minute. Now, your teacher may want you to round it off to the nearest decimal or whatever. So when we multiply 112 times pi, we're going to get about 351.858. Again, this is square meters per minute. So you have to find out what your teacher is looking for. They're looking for a decimal approximation or an exact value in terms of pi. All right. Let us continue on. By the way, do not use 3.15 for pi ever again. If you ever have to use pi, use the pi button in your calculator to get a much more accurate value when you're using that. So pulling out my calculator here. When I do 112 times, and for this calculator, the pi button is above my exponent button, so second pi, and it gives me a decimal approximation. You can see where I got my answer from. All right. Number 2. A hypothetical square grows so that the length of its sides are increasing at a rate of 3 meters per minute. How fast is the area of the square increasing when the sides are 14 meters each? So once again, we're going to have a picture. We're going to draw a square. I'm going to call each side x, meaning all 4 sides are x. And hopefully we know that the area of a square is literally x squared. That's where the word squared comes from. Now remember, both a and x are functions of t in this case, functions of time. So when I take the derivative, dA over dt, it says how fast is the area of the square increasing? So we're looking for dA dt in this case. This is going to be 2x and then dx dt. dx dt is going to be the rate at which each of the sides are increasing. And they tell us that. They say the length of the sides are increasing at a rate of 3 meters per minute. And they want to know how fast it's changing when one of the sides hits 14 meters. So we're going to go 2 times 14 times 3. And that's going to give us 84 square meters per minute. If you don't know some of these formulas, like the area of a circle or area of a square, hopefully you know. You can always look them up. Let's move on to number 3. A conical paper cup. So we are now to 3 dimensions. The first 2 were about area. A cone, which is a conical paper cup, is going to be in terms of volume. So a conical paper cup is 30 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 3 centimeters per second. At what rate is water being poured into the cup when the water level is 9 centimeters? So we have a lot going on here with this one. Let's start here with our cylinder, or pardon me, Mike, our cone. And we'll just ignore that. And overall, we know that the radius is 10 centimeters, and that the total height is 30 centimeters. Now, what we're going to do with this is we're going to break this down, because the level is rising, right? So I'm going to call this H, and I'm going to call this R. And H and R are changing, and they're changing with respect to time. And I want to draw the triangle out so we can clearly see it. This is 30 centimeters, 10 centimeters. And then we have our generic, let's use the blue, the generic R and the generic H. And I'm hoping that you can see that we have similar triangles. We have a small triangle here, and we have the larger triangle here. So in this case, what I'm going to get is I'm going to get R is to 10 as H is to 30. Now, they give me information about the water level, that's H. So they give me that dH dt is 3 centimeters per second. So what I want to do is I want to get R in terms of H, because I know I'm going to want to keep the H. So R in this case is 10H over 30, or 1/3 H. All right, now it is talking about volume, and the volume of a cone is 1/3 pi R squared times H. And I'm now going to replace R squared with 1/3 H. All right. So we now have 1/3, that becomes 1/9 when we square that. So this becomes 1 over 27 times pi times H cubed, right? H squared times H. So now I'm going to do my derivative. And they are looking for what is the rate at which the water is being poured into the cup. That's a change in volume with respect to time. Okay, we have a lot going on here. So they want to know when the water level or the height is 9. dH dt, we have 3 here. Let's dump it all in. H is 9. dH dt is 3. And this is our dV over dt. Let's move this up here now. And I'm not going to mess with the pi. I'm just going to leave it in terms of pi for now. And what I'm going to do is I'm going to go 3 times 81 times 3 divided by 27. That gives us 27. So this gives us 27 pi. And this is cubic centimeters per second. And if I plug that in, I get that. So it's about 84.823 cubic centimeters. So again, you'll need to find out for any given problem what your teacher prefers, the exact with pi or an approximation. Moving on. Number 4, a spherical balloon is deflated at a rate of 36 pi cubic centimeters per second. At what rate is the radius of the balloon changing when the radius is 8 centimeters? So now we're looking for dr dt. That's what we don't know. And they give us dv dt. In this case, is 36 pi cubic centimeters per second. So let's talk about the volume of a sphere. That is 4/3 pi r cubed. So we're going to take the derivative dv over dt, which we have in this case. So up until now, we haven't known this first part, but in this case, we are going to know this part. When I take the derivative, that 3 comes down and cancels with that 3. So I end up with 4 pi r squared dr dt. And that's what I'm looking for. So I'm going to have to dig that out here. And let's put this up here. dv dt is 36 pi. 4 times pi. R in this case is 8 squared. And then dr dt is what we are solving for. I'm going to first of all notice that the pi's right away divide out. So I'm not going to deal with the pi anymore. And that's going to give me 36 divided by 4 times 64. 4 times 64. That's going to give me a decimal, but I can convert that to a fraction very easily. I go to this calculator, I go to math and convert to a fraction. There it is, 9/36. One small thing I forgot, it says that it's being deflated at a rate. So this is actually a negative 36. Because it's getting smaller, right? The air is being let out of it. So we're going to end up with dr dt is equal to negative 9/64. And that is centimeters per second. And the decimal approximation of that is the 0.141. So again, centimeters per second. All right. Number 5. A spherical snowball is rolled in fresh snow, causing it to grow at a rate of 256 pi over 3 cubic inches per second. How fast is the radius of the snowball increasing? So we're going to have positive values in this case. When the radius is 8 inches. So once again, for this one, we're looking for dr dt. And they say it is growing at a rate, and they give us cubic inches, which means that is our dv dt. So let's start with the volume of the sphere again. 4/3 pi r cubed. And we'll take the derivative dv over dt is once again 4 pi r squared dr dt. Again, that's what we're looking for. They want to, so they tell us dv dt, they've given to us already. Is equal to 4 pi. R in this case is 8. dr dt. Once again, the pi's are going to reduce out. So when I divide all that, I'm going to get 256 divided by 3 times 4 times 64. And we're going to need to convert that to a fraction, which it looks like it's 1/3, which it is, which means dr dt is 1/3 inches per second. Number 6. A hypothetical cube grows at a rate of 8 cubic meters per minute. How fast are the sides of the cube increasing when the sides are 8 meters each? So now we're talking about a 3-dimensional square. I'm going to call each side x. And they give us dv dt right here. And they want to know dx dt. How fast are the sides of the cube increasing? Well, the volume of a cube is this, in this case, is length times width times depth is going to be x cubed. dv dt, which we have, it's right there, is equal to 3x squared dx dt. And they want to know when x equals 8, what we're getting. So let's do this here. There's 2 8s in this problem, so I can get a little confusing. The dv dt is the 8 here, equals 3. Now it's 8 meters squared dx dt. And dividing both sides by that is going to give me 8 divided by 3 times 64. And let's convert that to a fraction. There it is. This means dx dt is 1/24. And the unit on that is meters per minute. Number 7, it actually is very much like number 1. Except now we're looking for the change in the radius. So oil is spilling from ruptured tankers, spreads in a circle on the surface of the ocean. The area of the spill increases at a rate of 4 pi square meters per minute. How fast is the radius of the spill? So once again, in this case, we're looking for dr dt. And we already know dA dt, the rate at which the area is increasing. So once again, the area of a circle is pi r squared. So dA dt is here. dA dt they gave us, it's here, for pi is equal to 2 times pi times r, which they give us is 3 dr dt. Once again, the pi's will reduce out. That becomes 4/6, or 2/3. Meters per minute. I'm hoping you're kind of seeing a pattern as we're looking through these. All right, 2 more problems, then we're all done. Number 8. A 10-foot ladder is leaning against a wall and sliding towards the floor. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the base of the ladder sliding away from the wall when the base of the ladder is 6 feet from the wall? You'll want to read through that a few more times. Let's draw a picture. So we have a ladder It is 10 feet. And it is sliding down the wall, which means this is going that way. I'm going to label this X, and I'm going to label this Y. Okay, I'm hoping that we can see the Pythagorean theorem here. X squared plus Y squared equals 10 squared. All right, before I start doing derivatives and things, they tell me that the base of the ladder, this is an X value, is 6 feet from the wall. I need to get the associated Y value with that. So I'm going to do this. I'm going to go ahead and plug in here. 6 squared plus Y squared equals 100. This becomes Y squared equals 64. So Y is going to equal 8 when X equals 6. That comes out very convenient for us. So we'll tuck that away. Let's go back to here. X squared plus Y squared equals 100. That's the 10 squared. And I'm now going to do the derivative. Remember, X and Y are both functions of time, of t. This becomes 2x dx dt plus 2y dy dt. And the derivative of a constant we know is here. Now it says the top of the ladder is sliding down the wall. So that's going to be dy dt. And it's going down the wall, which means that's a negative 2 feet per second. It should be a 0, not a 1. I'm going to divide the 2's out. They're gone. So I'm just going to ignore them. And they want to know how fast the base of the ladder, that's down here, is moving away from the wall. All right, so we're looking for dx dt is what we want to know. So I'm going to go ahead and subtract that over. And I'm going to divide that X. D by dt. All right, so we are going to end up with our Y value, which is 8, negative 8 over 6. And dy dt is a negative 2, because remember it's going down. And that is going to reduce for us. Now that becomes a positive, and negative times negative is a positive. And so that reduces down to 8/3 feet per second. Now, there's 2 pieces to this one. Once we're given an X value, you have to dig out the associated Y value so that we can plug them in when we need to. And then we do the derivative of the function. All right, last problem for this video, I should say. A 5-foot tall person is walking towards a 17-foot tall lamppost at a rate of 2 over x feet per second, where x is the distance from the person to the lamppost. Assume the scenario can be modeled with right triangles. At what rate is the length of the person's shadow changing when the person is 10 feet from the lamppost? So let's draw a picture. So this is the lamppost, and then we're going to have also a person. They told us to define, well, let's put what we have. We have a 17-foot tall lamppost, and we have a 5-foot person. And they told us to define this distance here as x, And I'm going to define this distance here as y. So we have two triangles here. We have the little triangle, and then we have the big triangle. And I'm going to set this up. The y is to the 5 as the x plus y, right, this whole thing here, is to 17. And I'm going to go ahead. Now they tell us is walking towards this at a rate of here. So this is dy dt that they give us. So dy dt is 2 over x. Which means I need to solve for x here. So I'll cross multiply 5. And again, I'm solving for x, so I'll move that over. This gives me 12y equals 5x. So x is 12 over 5y. All right. So we are now going to end up with, I'm going to go ahead and take the derivative, dx over dt, which is what we're looking for. That's the length of the shadow. Dx dt is going to be, that's our, I'm sorry, I have this wrong. We're looking for dy dt. Dx dt is the negative 2 over x. That's what that is there. That's going to equal 12 over 5 dy dt, right? So we'll do the derivative there, dy dt. All right, so we're going to go ahead and dump into the dy dt. We're looking for dy dt, pardon me. We're going to go ahead and plug into the x, the 10. And we're going to multiply over the 5. Here we go. So we're going to solve for dy dt here and plug in, remember this is 10 feet. So this gives us negative 2 over 10 times 5 over 12. And this is our dy dt. And that is going to reduce it. You can see 2 times 5 is 10. So this is going to give me a negative 1/12 feet per second. All right. Now, it's negative. We tend to think this direction is positive. Because they're walking towards the lamppost, that's why the rate is negative, and both rates are negative because they're both getting smaller as they're getting closer to the light source. Anyway, I hope that helps.